Welcome to difference geometry class. Today we are going to deal about the orientation of surfaces. Mainly we will say that what is a connected surface, then how many orientations can be given to a connected surface, and if there exists any surface which cannot be orientable. So our discussion is based on three facts today. So the first one we are having the definition of connected. Definition. Connected. So when you will say that a space or a surface is said to be connected, a subset S of Rn plus 1 is said to be connected if for each point p comma q of points in S there is a continuous map say the map is alpha from some closed interval AB to S from some closed interval AB into S such that alpha of A equal to P and alpha of B equal to Q. Thus S is connected if each pair of points of S can be joined by a continuous but not necessarily smooth curve, which lies completely in S. That means suppose you have got a subset of Rn plus 1 as S. Now this S is said to be connected if for any pair of points PQ there should exist a path from P to Q. Say this is alpha and this alpha is defined from some closed level AB to S such that your alpha of A should start from P and end at Q. If such a path is existing for every pair of points in S, we will say that the set S is connected. So this is the definition of connected. So a subset S of Rn plus 1 is said to be connected if for each pair P comma Q of points in S there exists a continuous map alpha from closed level AB to S from some closed interval a b into S such that alpha of a should be equal to p and alpha of b should be equal to q. Thus, we will say that S is connected if for each pair of points S can be joined by a continuous but not necessarily smooth curve which lies completely in S. So, this is the definition of a connected surface or connected subset of Rn plus 1. Now, we are having a theorem. So, theorem 2. Let S subset of Rn plus 1 be a connected n surface in Rn plus 1, then there exists on S exactly two smooth unit normal vector fields n1 and n2 and n2 of p is equal to minus n1 of p for all p belongs to S. So this is the theorem. But this theorem says that we have got a surface S which is connected, then there exist exactly two smooth unit normal vector fields n1 and n2, and n2 of p is equal to minus n1 of p. So what this means is, suppose you have got a connected surface. Suppose you have got a sphere. Sphere is a connected one, right? So we have got a sphere here. Now in the sphere we can have two normals. So one normal is like this one normal. Now another normal can be given in the opposite direction, that means in this direction. See, like this. So in a connected surface we can give two orientations, right? That is, in short, that is, in a connected surface we have two orientations, and we have seen that one is going to be the opposite of other. So that's why we are saying that 1 and 2 of p is nothing but n1 of p. So how to prove it? Proof is very simple one. So proof, we know already one normal direction. What was that? Del f of p. So with use of that we are defining your n1. So let f from u to r and c belongs to r be such that S equal to f inverse of c and del f of p not equal to 0. Del f of p not equal to 0 for all p belongs to S. Then the vector field n1 on S is defined by first what it says is that the surface, definition of the surface. Now with respect to this surface, we have got a function f with the property del f of p not equal to 0 for all p belongs to S. Okay, now with respect to this, or you making use of this one, we are mentioning or we are defining a normal here defined by n1 of p equal to del f of p by norm of del f of p. Since del f of p is not equal to 0, this is well defined, comma p belongs to S. Clearly has the required property. Clearly has the required property. Now we want to define one more orientation, right? Now define n2 of p is equal to minus n1 of p for all p belongs to S. To show that these are the only two, to show that these are the only two such orientations, two such vector fields, comma, suppose n3 where another such vector field, then this is our usual procedure. Only two things is existing means we will say that suppose there exists one more thing, and we will get either this n3 equal to n1 or n3 equal to n2, right? Then for each p belongs to S, n3p must be a multiple of n3p must be a multiple of n1p. What is the reason? Since we know that the normal space has been spanned by del f of p, so that is a one-dimensional space. So n3p also belongs to the one-dimensional space, right? So it should be a multiple of del f of p. That means it's a multiple of n1 of p also. So since n3p comma n1p are members of one-dimensional space, del f of p, we will say that del f of p pub we can have, or else space we can represent as sp pub. Sp means tangent space, so it is sp pub, which is contained in Rp n plus 1. Thus what you're getting is n3 of p is equal to some multiple of n1 of p, where G from S to R is a smooth function, on S. Now since N1P and N3P are both unit vectors, what is the possibility of G? Plus or minus 1, right? Unit vectors. Your G should be, G of P should be plus or minus 1 for each P belongs to S. Now we will prove that this G of P is a constant one, right? So how to prove it? Okay, let it be the okay. Next, we will prove that since G is smooth, and S is connected, G must be a constant. On S. So once we prove this, we will say that G of S equal to either 1 or minus 1. That means your N3 should be equal to N1 or N2. Now how to prove this one? So given that S is connected, given S is connected, therefore there exists some G from S to R such that G is smooth, So let, instead of given, let G is connected and there is some G from S to R and G is smooth. So it's given that S is connected. Therefore, there exists some alpha from closed interval AB to S such that should condition alpha of A is equal to some P and alpha of B is equal to Q for P comma Q belongs to S. We are making use of the idea of connectedness. Now consider F equal to G composition alpha. Now G composition alpha is defined from closed level AB to R. Then this F is smooth. What is the reason? Since it is the combination of two smooth functions, so it is smooth. Then by the intermediate value theorem, there exists some C belongs to open interval AB such that, what should be your condition? such that f dash of this c equal to 0, right? That is f dash of z equal to f of b minus f of a by b minus a into equal to 0, which implies f of b minus f of a is equal to 0, or this implies f of b is equal to f of a. Since we have got p and q are arbitrary points, what you're having is f of b equal to f of a. So that means this implies what is f? G composition alpha of b equal to G composition alpha of a, which implies G of alpha of b equal to G of alpha of a, or that implies G of q, right? Alpha of b is q, right? See, alpha of b is q. So what you're having is G of q is equal to G of p. So this implies your G is a constant. Already we know that G is equal to plus or minus 1. So already we have G equal to plus or minus 1, which implies n3 of p equal to n1 of p or n2 of p. So what you're having is your n3 is nothing but n1 of p or n2 of p. So hence the theorem. So we have proved that whenever a surface is a connected one, we can have two orientations on it. Next is a definition. A smooth unit normal vector field. A smooth unit normal vector field on an n surface S in Rn plus 1 is called an orientation. It's called an orientation on S. It's called an orientation on S. So we can say that this is two orientable. So not according to the above theorem. According to the above theorem, each connected n surface in Rn plus 1 has exactly two orientations. So a n surface together with a choice of orientation is called an oriented n surface. So an oriented end surface means an end surface together with an orientation. Orientation means we are giving a uh, unit vector field on each of its unit normal vector fields on each of the points of the surface. Here is a remark. A surface on which there exists no orientations. So, does there exist any surface in which we cannot give an orientation? There exists certain surfaces like that, and one such surface is the Mobius band. Example is the Mobius band. BIUS it is. MOBIUS, Mobius band. So what's a Mobius band? Actually we will denote it as B, and this is an example of an unoriented surface. So we cannot give orientation to this surface. So before going, what is a Mobius band? Mobius band means, suppose you got a strip of paper. Now just you tilt the paper and paste at the end. You get a picture like this. Somewhat here. So you will get a picture like this. So when you're marking a center point means. Now the specialty of this band is that it has got only one surface. Specialty is that it has got only one surface. So let us see. I have posted here a small video of that. See, this is our Mobius band. I have twisted the paper and pasted. You can see a red ball and a blue ball. Now the blue ball is traveling along the surface. See, now it has touched the red ball. Now red ball started traveling. It's coming to the outward. Next again going to the inward direction. So that means it has got only one direction, one surface. At the previous, at the beginning of this video, you can see that the red ball is somewhat inside and that blue ball is outside. See, now the blue ball is traveling and exactly it is going in the same phase of the red ball. So this reveals that the Mobius band has got only one surface. Okay, now we are having the Mobius band here. So there is no smooth unit normal vector fields. There is no smooth unit normal vector field on B can be seen by picking a unit normal vector, picking a unit normal vector at some point on the center circle, and trying to extend it, and trying to extend it continuously to a unit normal vector field along this circle. That means, see, here we have got the Mobius band and its center circle. Suppose I am giving the direction like this. Like this, I am giving this side direction. See, if I am going like this means, see, up to here is okay. Now it is going inward direction. So inward direction, it may come like this. Okay, but when you're coming this side, it may go like this. So in this one surface, I'm getting exactly at one point I am getting two directions. So the direction is not defined. So that is the problem here along this circle. After going around the circle once, the normal vector is pointing in the opposite direction. So note that the Mobius band B cannot be expressed as a level set F inverse of C of some smooth function F from S to R with del F of P not equal to 0 for every P belongs to S. That means we have studied about the surfaces and the official definition of surface, but we cannot include this Mobius band in the category of surface as per our definition that we are going to note it here. For every P belongs to, thus an orientation on an N surface as in Rn plus 1 is by definition a smooth choice of oh, we have missed that one here, right? Here we should add, thus B is not a two surface. B is not a two surface as per our definition of surface. So this has to be noted. Just we cannot say that this is, so we should avoid this. So I should avoid this. Okay, let us see. Okay, some problem with my eraser, it seems. So just continue the discussion. So I'm cutting it here. So as per the definition of our surface, we cannot include our Mobius band as a inside the category of a surface. So definition: a unit vector in Rpn plus 1 comma p belongs to Rn plus 1 is called a direction at p is called a direction at p is called a direction at p. So whenever you are giving a unit vector at a point, it is called the direction at p. Thus an orientation on an n surface is a choice of a normal direction at each point of S. Thus an orientation on an n surface S in Rn plus 1 is a smooth choice of normal direction at each point of S. Okay, so what today's class we have discussed is, first we have got what you mean by a connected surface, then a theorem, that is in a connected surface we can give only two orientations. Next we have studied one example of a non-oriented surface, that is nothing but Mobius band, and we are generalizing the fact that as per our definition of surface, Mobius band cannot be included as a surface. Then also we are saying that it is a non-orientable two surface. Okay. Then the last one what we are saying is now we can modify our definition of orientation as it is the suitable choice of a normal direction at each point of the surface. So with this I am winding up today's session here. Thank you for your patient listening.